Okay, so you can see on this problem, we need to find the maximum positive moment at D for a variety of loads. So we're going to find the influence line for the moment at D. So I'm going to go ahead and make a quick sketch. Well, I'll do this first. So let's imagine that at D, I suddenly have this internal hinge, and then I apply positive moment to both sides. So how's this point D going to move? Is it going to move up or down? Up. Yeah, I think it's probably going to move up too. So then it'll hinge over here at E. It will seesaw over the C, hinge at B, and then move back to A. So there's our qualitative shape. So let me go ahead and then draw the influence line for the moment at D. I'll go ahead and re-sketch all this stuff. So I'll just transfer these lines down quickly. And then I'll redraw it. A little better to scale. So there's qualitatively what our influence line looks like. And also remember that the units of our influence line are in feet. Kind of squeeze that in there. Okay, so which one do you want to do? I think it would be easier to try to find that value. So if I'm interested in that value, that really means that I have to resolve my problem. How? Well, I've got my hinge. So I've got a pin, hinge, roller, then a long stretch out to another roller. So if I choose this position, that means my unit load is really where? Over D, which would be right about here. Right? Remember, the position on the influence line is the location of the unit of the load. So where would that be exactly? Well, this would be 5 feet, 5 feet, 5 feet, and 10 feet. Now, what am I looking for? Somebody's phone ringing? Is that just, it does sound like that. You hear that?
Yeah.
I think it's out in the hall.
Oh, it's in the hall? Okay. So what do I want? I want the moment at D, right? So I want the moment right there. So that means the free body diagram that I want to generate would be what? I'll cut it at D. So here's my moment at D. This is 10 feet long. What am I going to need? I'm going to need the reaction EY. And then, of course, my unit load would be right there at that point, too. So to actually calculate the moment at D for this position, what do I need? EY. How do I get EY?
In the Y direction.
Sorry?
We know the moments about B or 0, right?
So how do I find EY?
So EY,
So force it on Y direction, right? You know what?
Why can't you do that?
some moments were at A, then there's some portions in Y.
Okay, I just suddenly had a sneaking suspicion that this was not the right way to do this. Oh, this is why. This is why. Hold on. This is why. I forgot to include the shear at D. That's why you just can't sum forces in the y direction. So if before I do that, I step back even further, take it apart here at the hinge, and look at this free body. So I have EY, and that's CY. I'm still looking at my unit load right here. And then what's here? That's B. I would have some possible value there, BY. And I'll assume it's positive. Can I find EY from all that?
No.
Okay, let's go one step farther and look at the other side, which has BY. And then this has AY. So you have to really much take the whole thing apart. Now, looking at this whole set, and this one in particular, what's BY? 0. There's no load on this section, so we know that BY is 0. And once we see that, can I get EY with one equation?
Yeah.
Yeah, you sum moments about C. And if you remember, this was 5 feet. This was 10 feet. So I sum moments about C, I get minus 1 times 5 feet plus EY times 15 feet. So it looks like EY is 1/3. You good with that? Well, now I can put that here. How do I find the moment?
Some moments about.
Yeah, if you sum moments about the cut, what do you have? You have this moment, which is minus EY positive times 10. And what's EY? So that means that the moment at D is 10 divided by 1/3. So this value here is now, what's this value then by similar triangles? This is 5, this is 5, so it's okay? So it's a little bit different way of looking at it. You can get the qualitative view very quickly, and then you just have to figure all this out with statics, but for only one position. In this case, we chose this position. So now I have a full influence line. My influence line is complete. Now I can actually try to solve the problem. What does the problem say? What's the maximum positive moment that can be delivered due to a 4-kip load? So what's the maximum positive value? Right, so if I just look at the concentrated load, then its contribution to the moment is going to be 4 kips times 10/3 feet, which is 40/3, which is what, 13.333? And that will be kip feet. So that's the moment for that part. Okay? Now we already talked earlier that when you have uniform loads, you take the area under the curve, right? So the only difference here is that one of the uniform loads is called a dead load and one is called a live load. Now the dead load, we're going to assume, is applied throughout the whole structure. It may include like the weight of the beam or the weight of things that don't change. So you can't move it where you like. It's over the whole structure. So when I do the uniform dead load, I have to multiply this value of 200 pounds per foot times what? The area of the curve. I've got some negative area, I've got some positive area. So I'll do this one first. So they're all triangles, so it's going to be 1/2 the base. The base for the first one is 10 feet times the height, which is minus 10/3. So that accounts for this section. And then plus the second section, which is 1/2 the base. The base here is 15, and the height is positive 10/3. So you guys will have to compute that for me. I'm not sure what that is. And this is in pounds, so we need to convert it to kips. Anybody got a calculator going? Five. 8.33333, and that's positive, right? Is that kips?
I did multiply it by 200.
You did not? Ah.
Should be 1666. 1,666.
And that will be kip feet. Okay, now here's question. So here's the thing that's different. When you have a uniform live load, what's the difference between a live load and a dead load? They move around.
Right.
So I want to move my live load around this structure so that it creates the biggest effect for the positive moment. That would be only the areas of the graph that are positive. So I only want my live load to extend here. So I'll go back now and compute that. So the live load has a 300 pound per foot load. And then this time, I'll only take the area of the positive part of the curve. So that'll be 1/2 base, which is 15 feet, height, which is positive 10/3. So what's that? 50, 25. I'm sorry? 7.5. So what I have to do is add all of those up. So the moment at D would be what? You add that together, you get what? 15. So that's 22.5. So that's the maximum moment at D for this loading. Now, what does that loading look like? Well, let me redraw the beam real quick. Oops, sorry. Is it?
Yep.
How much time do I actually have? I think I have just enough time. So here's my beam. So my dead load extends the whole length, right? So there it is. I'll say dead load. My live load only extends over this part of the beam. And then where does my concentrated load appear? Over D, which is about here. So that's the loading pattern that creates the maximum moment at D. Any questions about that?